Okay, it looks like a good amount of attendees have joined, so we're going to start. I just want to go through a few housekeeping rules before we begin. If you have any questions, please leave them in the chat box below. This session is being recorded and you will receive a copy of the recording after the webinar and a follow-up email. We are going to launch 2 poll questions, so please stay alert and answer to the best of your ability. Your speaker for today is Ultimaker's application engineer, Arvind Krishnan. Arvind, take it away.
Hey guys, once again, this is Arvind Krishnan. Good morning from California. I'm an applications engineer at Ultimaker, and we have some exciting content to share with you today. So we will be focusing on designing for Fused Filament Fabrication, or FFF. This is similar to designing for additive manufacturing, but specific to the FFF process. So let's go ahead and get started. I'm going to start off with showing you an application. Now, the video might be a little choppy on your end, and I would like to apologize for that, but we're going to talk about this application from VAR. We worked in conjunction with them to tweak this design for FFF manufacturing. So in this video, the mechanic places the rear alignment tool on the brake light and clamps it down. After that, he attaches the carbon rods to create a horizontal plane to the rear wheel axis. Then the mechanic places a string on the carbon rod and adjusts the wheel to the correct alignment. And I hope you got an idea from the video. So we want to look at this application in a little more detail. This is what the tool looks like, and this is the preliminary design that their engineers came up with. So some of the requirements is high strength, of course, and it needs to be clamped around the rear brake light. So we got some feedback from the mechanic who was actually using this, and he came up with the following topics of concern. The application was very big and unnecessarily heavy, is what he thought. The design had some sharp corners, and he was hoping for a more ergonomic design. And lastly, since this application was going to be outward facing, they wanted to add some branding to make it more recognizable. And what we'll do is we will revisit this at the end of today's webinar and look at what changes to the design we made. But it's a good time to bring up our first polling question as well, because I'd like to kind of get an idea of what you guys think is should be changed in this design. So Trisha, I'll go ahead and get you back in. Can you show us the first polling question?
Absolutely, Arvind. Launching now.
So you should see a poll question show up. Which of these concepts would be useful to change this design for additive? Avoiding overhangs, using chamfers instead of fillets, hole size and gap guidelines, and lastly, modularity, where you take one part, divide it into separate parts. So if you guys could please go ahead and choose an option on your screen.
It looks like we're still collecting responses, so just another minute, Arvind.
Sure. Let's give them some time to do that, and then we'll get started again with the agenda.
It's still climbing, so let's just give it a few more seconds.
Sure.
Okay, it looks like we got majority of the vote, so I am going to close the poll.
Sure.
And I'll share the results. Arvind, let me know when you want me to hide the results.
Sure. It looks like, go ahead. So it looks like most people think avoiding overhangs, is that right?
Correct.
Okay. Okay, great. Well, we will go through today's webinar and then get back to this question and see what other changes we can make. Okay. Thank you guys for your response. So an agenda for today, we looked at the polling question, right? An agenda for today, we will begin with a comparison of FFF to other manufacturing methods like CNC and injection molding. This is to understand how different FFF is compared to these methods. Now, like any manufacturing process, FFF also has its set of constraints. Once understood, you can take it into account in your design process to get better 3D printed parts. Finally, we will explore some best practices. When followed, your designs will be lighter, more repeatable, should print faster, and be stronger in the desired direction. So we will get started with comparing it to other manufacturing methods. So we'll look at CNC machines. CNCs are typically used to cut metal stock into a final desired shape. These come in a variety of shapes and sizes. They go all the way from 2 axes to 6 axes, typically increasing in cost and capability. This is a subtractive technique where the machine removes material. Next up is injection molding, where plastic pellets are melted and squeezed into a mold under high pressure, forming the shape of the empty cavity as it cools down and solidifies. And we will be comparing this to 3D printing, which is an additive process where material is added layer by layer to build a part. So comparing it to CNC, Ultimaker's 3D printers are typically office-friendly machines. You can have it sit right beside a designer or an engineer, and this helps you create quick functional prototypes of your part as soon as you complete designing it in CAD. This is also true for small batches of production. For a CNC machine, you could have a much longer workflow. Even if there is an in-house machine shop, drawings have to be made, approvals needed, revisions to the drawings, and you need a CAM software to create G-code. The machinist must then find a gap between producing production parts to create your prototype. So if you're using an external vendor, this process could take even longer. Now, another benefit of 3D printing is, theoretically speaking, complexity is free when you're 3D printing a part. A more complex design need not necessarily take longer to print or cost more. Now, this is not the case with machining. In addition to an increased amount of time, sometimes a tool change is needed as well, which requires manual intervention. Now for the flip side, when doing batch production, cycle times of FFF is going to be longer. Once you've finalized your product and you have G-code to manufacture it, CNC machines are expected to produce parts at a faster rate. And this is true in most cases. If you have one expensive CNC machine, comparatively, having a fleet of 3D printers can simultaneously create 3D printed parts could be faster. Also, if 1 out of your 10 3D printers are down, you still have 90% of your production capacity going. Advanced applications sometimes need advanced material requirements that cannot be met with common Ultimaker filaments. And in these cases, metal parts are just needed, for more strength, other things like chemical resistance and vibration requirements, all of those. I do want to point out that Ultimaker is an open material platform, and many of our third-party materials fulfill these expanded requirements. So do take a look at that as well. Continuing on to injection molding next. The first step to injection molding is to create a metal mold. This process takes time and is cost prohibitive as well. If the quantity of parts needed are fewer, FFF could be a better alternative. Injection molding also requires a level of expertise, typically gained with experience. If the final part is not as expected, there are hundreds of different process parameters that can be altered. Injection molding also has design constraints that you need to adhere to. So once you create that mold rework is expensive. The original design cannot be modified significantly, whereas in 3D printing, modification does not cost any money or time. Cycle times with FFF is typically longer. The biggest benefit of injection molding is the fast production times for large quantities of parts. Hence, typically 3D printing is recommended only for low volume batches of end-use parts. Do note that 3D printing can create complex geometries where you can combine multiple injection molded parts into one 3D printable part. So when you're comparing times, you could potentially save time in assembly and quality control as well. The surface finish of an injection molded part is definitely smoother than an FFF print. Ultimaker's machines go down to 60 micron layer heights, or about, it's less than 2,000ths of an inch with recommended settings. And there are post-processing options to smoothen it as well. But at the end of the day, it is a layer by layer process. So now that we did that comparison, let's talk about some of the constraints. Like every manufacturing method, 3D printing also has a set of constraints that you should adhere to. Let's take a look at them. The first one here, a relatively obvious one. Your 3D prints can only be as large as the build volume. Ultimaker's S5 is 330 by 240 by 300 millimeters, or 13 by 9.5 by 11.8 inches. What we've realized is this build volume is large enough for 80% of our customer applications, while still maintaining a high level of accuracy. If your design is bigger than this build volume, consider modularizing your design, where you divide a part up into multiple parts, and then you could simultaneously print them on different machines. Create locating features to combine them later on. Since FFF is a layered approach, designing the orientation to print early in the design process helps you make design choices, alignment of text, snap features, etc. Now, the mechanical properties are anisotropic in nature. As seen in the picture on the right, if the tensile test sample is printed, the stronger, so if the tensile test sample is printed flat, it will be stronger in the tensile direction, as the layers would be aligned along the load path. The orientation directly affects where the overhangs are and whether the model will need support or not. This affects the print time, the post-processing time to remove the support, which faces have better surface finish, and again, all of these depend on the orientation. Continuing on, let's get into more details on overhangs and support. FFF printed parts are self-supporting up to about 45 degrees. This is different from some other 3D printing technologies that need support for all angles if it's above the vertical. Overhangs below 45 degrees should be supported with support material below it. The picture on the right shows a PLA print with different angle overhangs printed without support. So let's go ahead and look at what the underside looks like when there's no support. If you notice, the surface quality is good until about 35 degrees to the horizontal, but it worsens as we go to lower angles. There are three options for support. The first one is a breakaway support material that we have. This is compatible with most materials and typically peels off in one neat piece. There's also PVA support. Once printed, the entire part is submerged in water where the PVA dissolves away. Finally, you could also use model material as support and break it off later on. Do note that we have some interesting third-party support material as well that you could avail of. There is a constraint on how small you can print. This is dependent on the nozzle size, and Ultimaker's smallest nozzle is a 0.25 millimeter diameter nozzle. Typically, you would need at least two lines of thickness in a wall, and hence a minimum wall thickness of 0.5 millimeters is recommended. Once again, the minimum layer height is 60 microns based on recommended settings. Let's talk about bridging. FFF printing doesn't need support when bridging materials between small gaps. The example part on the right is printed without support. As the gap becomes bigger, the material begins to sag. As a general rule of thumb for most basic filaments, a 10mm gap is good to print without support. Now with active cooling and optimizing some other settings, we have printed up to 25mm with tough PLA on an Ultimaker machine. In your screen on the bottom left, we posted some values in the table based on the print core that you use. So do know that it does change with that as well. Now that we've looked at some of the constraints, let's go ahead and switch our focus to some design guidelines for the 3D printing process. We'll start with wall thickness. So once again, minimum height of 0.06mm and minimum wall thickness of 0.5mm. This is dependent on the nozzle. So the smallest nozzle that Ultimaker has is 0.25. If you're using the 0.4 or the 0.8 nozzle or the 0.6 in terms of the CC tip, your prints will be much faster, but the minimum height and thickness will increase. Adding text is a big advantage. Maintain a maximum depth of 2mm when debossing or embossing so that the text is legible and there's no stringing on the inside. Remember a couple of minutes ago, we spoke about breakaway support material? When you're debossing, consider using this and filling the inside gap with the breakaway support material. When removing the support from other regions during post-processing, just don't remove it in this region. For a dark colored 3D printed part, the contrasting support material text looks really clean and stands out. Minimum hole sizes. So this refers to the smallest hole that can be printed without the hole being filled in with material. Minimum hole diameter is dependent on material and settings. As a rule of thumb, do not design 3D printed hole features to be smaller than 2mm. If you need accurate holes, if those are required, it is recommended to design the holes smaller than intended and post-process it with a drilling operation. A minimum pin diameter of 2mm is also recommended. When two or more components are printed together, as seen on the right, maintain a gap of 0.6mm to ensure that the part will move after printing as well, if it's an assembly and you're printing it together. Next, let's talk about warpage. So in general, you want to avoid sharp corners. These can be modeled in CAD, but the print may warp if you print it with sharp corners, as seen in that star shaped in the bottom left. Increasing the area that the surface is in contact with the bed will decrease the likelihood of the part warping. We do have some more examples on the right. The star-shaped design, let's look at those 4 images on the right. The picture on the right side has fillets and is less likely to warp. Adding fillets at the corners of each of these edges will ensure that the print completes without warping. Sometimes when printing without a raft, you may notice that the first layer is slightly larger than the rest. This is due to a phenomenon called elephant's foot. While rarely noticeable, it decreases the tolerance of functional prototypes. A simple solution to fix this is adding a 45-degree chamfer on the bottom edge of the print. The effects of elephant's foot can typically be negated with this. Also, for the bottom layer, check the edges on the right. You see 4 options on the right side, right? The first option has a 45-degree chamfer. This is the top left. And this can be printed without any support. The second option is even better. There's a 45-degree chamfer to start with, but it ends with a fillet for a smoother finish. The third and the fourth option will ideally need support. And when you add support, there's nothing wrong with it, but it typically increases the print time. Your post-processing time would increase as well. And if you could avoid it, it's better to avoid it. The fourth one, which is only a fillet, the face won't look as good if you don't use support. The surface finish would be typically poor. Let's talk about ribs and gussets real quick. Here is a whole bracket with a shear load on it, and it can be reinforced in a couple of different methods. So the leftmost option has not been reinforced. The middle option would be has 4 ribs and is typical for injection molding. The design reduces the amount of change in the thickness, which affects the shrinkage amount when injection molding. The third option on the right produces the least amount of stress, but the thickness difference is big and is gradual and will produce defects if injection molded. However, it is perfect for 3D printing. There are no stress concentrations because of better load distribution. We did a stress analysis to compare these results. Let's go ahead and look at them. If you compare the maximum stress value of these 3 options relative to each other, the second option has a smaller region of high stress, even though the value of the stress is relatively the same as the first one. The third option on the right has a maximum stress value about half of the first 2 designs. It has a better load distribution as well, and with FFF, it can be 3D printed as well. At this time, I want to revisit the application that we started off with. Some of the design changes that we made, we had a smaller overall width of the tool and increased the amount of outer wall lines for more strength. In this webinar, we spoke about bridging, and bridging distance was used in multiple areas to print without support. Now, support is needed in some areas. One of them is the overhang on the right, and the overhang on the top, and then above this logo, there's a bolt that goes in on the side, and when printing, that needs support as well. 45-degree angles were used in most places to reduce the amount of support usage. You can see some slots on the inside of this part. We have separate 3D printed parts that go in there. I will talk more about that in the next slide. This part was oriented such that the logo on the right was flat on the bed. And lastly, we used a third-party Clarion PA666 material. It's a composite with a 20% carbon fiber infill for higher strength. Let's get into a little more detail here. The picture on the left is what we spoke about in terms of adding a chamfer and a fillet. This decreases the stress and improves the ergonomics and doesn't need support as well when printing it. The picture on the right shows you the empty slots, which were filled in with a bright red TPU print. Now, these are the points of contact with the metal piece and experiences more wear. Hence, a wear-resistant material was used. Also, when this material eventually wears out, only these TPU parts have to be replaced instead of the entire 3D print. This is the modularity that we spoke about. As we conclude this webinar, what about more advanced topics along this track? So this was just an introductory webinar. In the Design for FFF track, we'd like to hear from you on what advanced topics you would find beneficial. So I'd like to bring in Trisha again for our second polling question. Trisha, could you go ahead and put that poll up?
Absolutely. I am putting it up now. Everyone should see it about now.
Okay. So let us know along this track, what would you like to see more of? Yeah, so is it going to be dual material prints, topology optimization, which is one of my favorites, part consolidation, or vent to separate parts or modularity, as you saw with that example that we just showed? So please go ahead and select one of those options.
Let's give it one more minute, Arvind. It looks like people are still voting.
Sure.
Okay, it looks like we've come to a standstill, so I'm going to close the poll and I'll bring up the results.
All right, looks like topology optimization is a clear winner here. That's good to see. But dual material prints and modularity is also up there. So that's nice. We'll definitely take that into account. Um, I hope you enjoyed this webinar. We do have some of what I spoke about today in a white paper. So if you take out your phones and scan this QR code, you should be getting a link to a white paper. I'll keep it up on the screen for a little bit. I do want to inform you that we will be sending this out once we in the follow-up email with the webinar recording. So I'll go ahead and open the floor up for any questions. I'll leave the QR code up for just another couple of seconds. All right, great.
Perfect. Thank you, Arvind. A few questions did come in that I will read off to you. The first one is, are the supports automatically generated if overhangs are detected? Is it adjustable?
Yeah, so are the supports automatically generated? Yes, so the Cura slicer that we use, you bring your part in and then you can define the angle below which you want support. And any overhangs that are there that are above that angle threshold will have support. And they are automatically supported or they are automatically generated. Cura does give you the flexibility to change some of the settings based on the support, and you have that flexibility when you process the part.
Great. Another question is it possible to check the design in Cura before starting to print?
Yes, so Cura gives you the option of previewing your design, and also once you process it, previewing what each of the different layers look like. What is the head going? What path is the head going to take as it traverses to build your part layer or one layer at a time? And yes, you can see that you can decide the orientation as well in Cura. Yes.
Great. The next question, is it possible to check physical and chemical properties of third-party material?
Yeah, so of course, Ultimaker is an open material system, and there are some really good third-party materials out there that can be used as long as they're a 2.85 millimeter filament diameter. The marketplace that Ultimaker has some of these materials available, so you could choose what materials you want based on that. Now, this marketplace is available inside of Cura and also in our website. The technical data sheets for these materials are also available along with the name of the materials and other details. So you could check things like what the yield strength is, what is the strength in different directions, what different liquids or fluids are they chemically resistant to, and all sorts of details like that.
Makes sense. We have one final question. How
Sure.
to increase the strength or stiffness of a 3D printed part?
There's a couple of different methods to do that. The first one that I like is to increase the wall line counts, as we did with that VAR application. Typically, the thought process is to directly go to infill percentage, but more than infill percentage, increasing the amount of wall lines on the outside will increase the strength because you're placing it furthest away from a mechanical engineering standpoint, and also increasing the amount of top and bottom layers. So this will, once again, these first two options that I spoke about it's almost like 100% infill in certain areas, like the outsides of the part. And of course, increasing the infill increases the strength as well. So those would be the three things that I would change to get a stronger, stiffer part.
Great, thank you, Arvind. Thanks for being our speaker today.
Absolutely.
If anyone put in questions later in the webinar, we want to stay timely, so we will answer them in a follow-up email. As discussed in the beginning of the webinar, this is being recorded, so you will receive a copy of this recording also in the follow-up email. Us as an Ultimaker team would like to thank you for joining, and whether it's breakfast, lunch, or dinner, have a good rest of your day. Thanks again.